This is the 6th lecture on the waves topic. In this lecture, we're going to start looking at sound waves. This lecture is going to cover textbook section 17.1 to 17.5. First of all, a quick recap of the most important points from last lecture. We looked at standing waves. We saw that they had the form y is equal to 2a sine kx cos omega t. We saw that they can be split into a spatial and a temporal part, and that particles that make up the medium undergo simple harmonic motion with the amplitude 2a sine kx. We saw that nodes were points on the standing wave with zero amplitude, and that these were half a wavelength apart, and that antinodes were points on the standing wave at which the maximum displacement occurs. These were also half a wavelength apart, but offset so that the antinodes are halfway between the nodes. We saw that on the string there's boundary conditions. Because the string is tied at the two ends, it has to have nodes at these points. So this leads to a series of allowed frequencies on the string, or resonance frequencies, given by the natural frequencies are n over 2L root tension over mass per unit length for the string. So these are just integer multiples of the fundamental frequency, which is the frequency that it oscillates at when n is 1, when there's just one loop, and the length of the string is half a wavelength. So onto new material, sound waves. These are longitudinal waves. They can move in 3 dimensions. They need a medium or material to travel through. So all the space movies where there's a loud noise when something blows up are incorrect because there's a vacuum there. There's no material for the sound to travel through. As sound waves travel through air, they can move the molecules that make up the air, creating high and low pressure regions. And they can be modelled as a sinusoidal wave, like on the string. So a drum, for example, makes sound because when you hit its top here, the top starts to vibrate. That causes the air particles around it to vibrate, and that vibration is a sound wave which gets carried to your ear. Violins, when you move the string across, you start the strings vibrating. They then cause the body of the violin to resonate, and that's how we hear that sound. So this is an example that we'll be considering quite a lot during this lecture. We've got a tube filled with a gas, and we've got a piston on the end. We can move the piston in and out, creating sound waves in that gas. The regions of maximum pressure, where we've got lots of particles, are called compressions, and the regions with low pressure are called rarefactions. There's a wavelength between each of the compressions and also between each of the rarefactions. So we're going to assume now that this piston is being moved in and out with simple harmonic motion. So briefly, just a quick description of how the ear works. We've got the earlobe here, which collects the sound and channels it into this auditory canal, where the pressure differentials caused by the sound wave cause your eardrum to vibrate. This vibration is carried through these bones here to the cochlea, and the cochlea is filled with a fluid, and along the surface of the cochlea are little hairs that are attached to nerve endings. So when these hairs start to move due to the sound, the nerve endings detect it and send this as a signal to the brain, and that is how we hear sound, very briefly. So quantitatively, remember we had our piston moving in and out with simple harmonic motion. So let S of xt be the position of a small element relative to the equilibrium position. So this is talking about a little bit of gas. So S of xt, the position relative to equilibrium, is equal to S max cos kx minus omega t. So it's moving back and forth around its equilibrium position with simple harmonic motion. And we can use this to derive an expression for pressure. Just to give you a bit more of a visual of what's going on, here we've got a plot of the displacement from equilibrium versus the position. So you can see as time passes, the displacement from equilibrium changes. And down the bottom here, we've got the actual plot of where the particles can be found. So when at this point here, the this particle is at equilibrium, so it hasn't moved. This particle has moved a little bit to the left because it's got a negative displacement, and this one's moved a little bit to the right. So they're all close to this equilibrium position. At this point here, the particle right here will remain right there because it hasn't moved from its equilibrium position, but this particle has moved away to the right and this particle has moved away to the left. So this is where they're stretched out. So the nodes on this graph here correspond to the compressions and the rarefactions in the actual particles. So this is going to be a maximum pressure here because we've got the maximum density of particles and another maximum pressure here. So the maximum pressures actually occur when the position from equilibrium is equal to 0. But the rarefactions also occur when the distance from equilibrium is equal to 0. Okay, now let's do some derivations which involve pressure. Now the initial volume of the undisturbed gas here is given by the surface area times delta x, the width of the gas increment that we're considering. Now after we apply a force and there's a wave travelling along which moves this entire part of the gas to the right a bit. But the left-hand side here moves a little bit further than the right-hand side, so it actually gets a bit bunched up. To get the change in the volume, we've got the area, and then we need to consider how this length has actually changed. So the left-hand side has moved a distance s1, the right-hand side has moved a distance s2. So the change in the width is s1 minus s2. Okay, now I need to use this definition. B is the bulk modulus, and it's defined as the volume stress over the volume strain. This is a property for materials which describes how they respond to a force which is applied to them. So just by definition, the volume stress is equal to the change in the force over the area, and the volume strain describes how the volume of the object changes, so the change in volume over the initial volume. So change in force over area, that's just equal to change in pressure over area, because pressure is just force over area. Delta V on VI, we're just leaving. And so we can see that the change in pressure is equal to B times delta V on VI. Okay, now we're just going to substitute in. Delta P is equal to minus B, and we said it was delta V on VI. Delta V is A delta S, and V is A delta X. So now the A's will cancel out, and taking the partial derivative, so replacing this capital delta with a little delta to indicate that we're taking just a very small increment, we can write this as minus B ds dx, and then substituting in, we said S was equal to S max cos kx minus omega t. They're moving with simple harmonic motion about their equilibrium positions. So then taking the derivative of this, our negatives cancel out because we get negative sine kx minus omega t, and this k has to be put out the front as well. So this gives us an expression for the pressure change in terms of the equilibrium displacement. So a quick quiz. If you blow across the top of an empty soft drink bottle, a pulse of sound travels down through the air in the bottle. At the moment the pulse reaches the bottom of the bottle, what is the correct description of the displacement of the elements of air from their equilibrium positions and the pressure of the air at this point? A, the displacement and pressure are both maximum. B, the pressure and displacement are both minimum. C, the displacement is 0 and the pressure is maximum. Or D, the displacement is 0 and the pressure is minimum. Okay, well, to answer this one, we saw that the pressure went as a sine function while the displacement went as a cos function. So when one's 0, the other one's going to be a maximum or a minimum. So A and B are both necessarily wrong because they're not both maximums and minimums at the same point. Okay, now at the bottom of the bottle, the air particles aren't actually moving, and we actually have high pressure because that's where all the air particles gather when they're reflected from the end. So C is the correct answer. The displacement is 0 and the pressure is maximum. At this point in the lecture, we stopped to do a thermal inventory test to see how much you'd learnt during the thermal topic. The next slides are going to differ slightly from what was presented in lectures. In lectures, we did not go through and derive the velocity of sound because we'd already done it for the velocity on a string. We also didn't derive the power carried by a sound wave because we'd already done it on a string. So if you want to see these derivations, they are in the lecture material that is provided following this slide. If you want to skip over them, then that's fine. You're not going to be tested on these derivations, but I think it's good for you to know that they do exist, so you don't have to trust me that these work. You can see where they come from. Okay, now we're going to derive an expression for the speed of sound. This expression ends up being very similar to the speed of the wave on the spring expression. So imagine that we have some initial state. We've got an initial pressure, P, applied on the surface area, I, and we're considering a piece of gas with a length V delta T. So V is the speed of sound in this medium, so the delta T sets the length that we're using. The final state, we now apply a force. This creates an unbalanced force, so delta P is the unbalanced force, the resultant force, and this region is compressed. It now has a change in width of Vx delta T, where Vx is the speed that all the gas particles are moving with. So at the end of time, delta T, they're all moving with this speed Vx, which means that they've all moved in from the end, a distance Vx delta T. Okay, so now what we can do is use our impulse momentum equation. Impulse is equal to the change in momentum. We'll start by calculating the impulse. The impulse is equal to the force times the time. Now this is the resultant force. The resultant force is due to this unbalanced pressure here, the delta P. So force is equal to area times delta P. And then delta time, we've got our delta time here, and this is all going in the I direction. Okay, but from before, we know that delta P is equal to minus B times the change in volume over the initial volume, so that's minus B. Now the change in volume we said was minus Vx A delta T, and the initial volume was just the VA delta T. So the A's will cancel out and we'll end up with B Vx on V. So this gives us that the impulse is equal to, just having a look, we've got A delta P delta T, so we've got A and then the B Vx on V delta T I. And we know that impulse is also equal to the change in momentum. So the change in momentum is just the mass times the change in volume. The mass of the gas is equal to the density of the gas times its volume. And the change in its velocity is the Vxi minus the 0. So that's rho V Vx, because the initial volume was the VA delta T. Here's the Vx and there's our I. So now what we can do is just equate these two because of impulse. So we've got AB Vx on V delta T is equal to rho V Vx A delta T. Almost all of it cancels out, the delta T's, the Vx's, the A's, and we end up with V, the velocity of the sound in the medium, is equal to the square root of the Young's modulus, the bulk modulus, over the density. So V is equal to the square root of the bulk modulus over the density. In general, we've got that the velocity of sound in a medium is equal to the elastic property of the medium, in this case the bulk modulus, in this case the tension, over the inertial property, which in this case is the density, and in this case it's the linear density. So the speed of sound is actually dependent on temperature. Why? Okay, so let's try and derive a similar equation. Okay, so we've just shown that the velocity is equal to the square root of B over rho. Now, the density is actually dependent on the temperature, because we've got density of a gas is equal to the number of moles of a gas times the molar mass over the volume, and we have PV is equal to nRT. So that tells us that N over V is equal to P over RT. So we can write that the density is equal to P over RT times the molar mass. Now the pressure, this is just the outside pressure, so this is the atmospheric pressure, it's not changing. The molar mass of the substance that it's going through is not changing. R is a gas constant, so it's not changing. So we can say that the density is proportional to 1 over the temperature. That's the only variable in this equation. The bulk modulus for a given material also does not change. So we have that the velocity is proportional to 1 over the square root of the density, which is proportional to, because the density is proportional to 1 over T, this is proportional to the square root of the temperature. So this means that we can write V1 over V2 is equal to the square root of T1 over T2. Or the velocity at some temperature over the velocity at 0 degrees C is equal to the square root. Now this was the ideal gas law. So these ones are in kelvins. So this is T, let's call it Tc plus 273. This is the temperature in Celsius over the temperature at 0 degrees C, which is the 273. So this gives us V is equal to V0, the speed at 0 degrees C, over 273 over 273 is the 1, plus then we've got the Tc over 273. So that's derived, this equation here. This is the velocity of sound in air at 0 degrees C. This needs to be measured or told to you. Okay, so this table just presents the speed of sound in various mediums. As these gases get heavier, you can see the speed of sound decreases as we'd expect, because as the density is increasing, as this is increasing, this needs to decrease. With liquids, we can see that the speed of sound is higher in liquids and then it's even higher in solids. For liquids and solids, you would need to consider the bulk modulus and how that's going to affect it as well. Okay, so let's have a look at how pressure and displacement are related. We can consider the maximum values. So we've said that the change in the pressure is equal to BKS max sine Kx minus omega t. Now the maximum value for this is going to be when this is equal to 1. So the maximum pressure differential will be BKS max. Okay, now the bulk modulus isn't an especially useful thing to work with, so let's try and change this around a bit. We've said that the velocity is equal to the square root of B, the bulk modulus over the density, which tells us that the bulk modulus is equal to the velocity squared times the density. So we can replace this term with that. K is equal to 2 pi over lambda. Lambda is equal to the velocity over the frequency. So we can write this as omega over V. So let's make these replacements. We've got V squared rho times omega over V times S max. These V's cancel and we end up with V rho omega S max is equal to the maximum pressure differential. The reason for doing this is just that the density, the velocity and the angular frequency of the sound wave are easier to measure than the bulk modulus. Okay, so let's consider the intensity of periodic sound waves. So we've said previously that waves carry energy and sound waves are a type of wave, so they carry energy as well. So let's imagine a piston moving backwards and forwards and creating sound waves. As it does that, as it moves backwards and forwards, it's doing work on the gas, and work is given by F dot dx. So work is a form of energy. So the rate of work done gives us the power. So that gives us the rate at which we're putting energy in. So power is equal to F, and now is the x, which is changing with time. So we have Vx. That's the derivative of x with time. Okay, now you don't need to be able to reproduce this derivation, but just so that you've seen it. Power is equal to F dot Vx, that's what we just said. Now the force applied, the resultant force was equal to the pressure differential times the area, and then we have to take the derivative of the equilibrium displacement to get the velocity of the increment that we're considering. So we've said that delta P is equal to PV omega A S max sine Kx minus omega t. So we're just substituting in for that, and we're just substituting in for this S as well. We've got S max cos Kx minus omega t. Now all we need to do is take the derivative of this. When we do that, we get omega S max sine Kx minus omega t. And so then multiplying these two together, we end up with rho v omega squared a S max squared sine squared kx minus omega t. So this gives us the power which is transferred at any point in space and time. Now, what we're really more interested in is the average power which is transferred. So what we're going to do is we're going to work out the average value of this thing over one period. If we then divide that by one period here, divide it by the time it takes for one period, that will give us the average amount of power. So all we do now is we integrate this term here because it's the only one with a t dependence over one period. It's just a standard integral, and it actually turns out that this is equal to a half, so we can replace this with a half. And so the average power is given by a half rho v omega squared a s squared max, and the intensity is always just the power over the area. So this power spreads out over an area, and that gives us our intensity. So for this case, with the wave moving in the x direction, we have the intensity is just a half rho v omega s max all squared, or in terms of pressure, we can replace this rho v omega s max squared with a delta p squared, and then we just have to divide by the 2 rho v. We can get the intensity is proportional to the maximum pressure in this form. Now, usually sound waves are traveling out through three-dimensional space, and they're traveling in the same velocity in each direction, and so they end up being spread over the surface area of a sphere. So generally, in this intensity formula, the area that we're considering is 4 pi r squared, the surface area of the sphere. So to practice using these equations, try homework set 6 for Phys 1121 students, 6, 7, 8, 12 and 13. For 1131 students, questions 7, 9, 10, 12, 15 and 16. Okay, quick quiz, this is quite difficult. A vibrating guitar string makes very little sound if it is not mounted in the guitar body. Why does the sound have greater intensity if the string is attached to the guitar body? A, the string vibrates with more energy. B, the energy leaves the guitar at a greater rate. C, the sound area is spread over a large area at the listener's position. D, the sound area is concentrated over a smaller area at the listener's position. E, the speed of sound is higher in the material of the guitar body. Or F, none of these is correct. Okay, now this one's really quite hard. A, the string vibrates with more energy. No, when you pluck it, you give it a certain amount of energy, and that's the energy it has. B, the energy leaves the guitar at a greater weight. Well, actually this does happen, because as the string's vibrating, it causes the guitar body to resonate, and so it is transferring extra energy to that guitar body, and so you are losing energy at a greater rate, which is why you have a louder sound. Because you're losing it at a greater rate, it's going to run out sooner. So whereas the plucked string not attached to the guitar body would keep vibrating for a very long time, the guitar string is going to vibrate for a much shorter time. C, that's not true, because the area that we're considering would be the listener's eardrum, so that hasn't changed. D, same thing. E, the speed of sound is higher in the material of the guitar body. True, but it doesn't affect the intensity. And F, none of the above. Well, B actually is correct. Okay, question. A sound wave propagates in air at 27 degrees C with a frequency of 4 kilohertz. It passes through a region where the temperature gradually changes and then moves through an air at 0 degrees C. Give numerical answers to the following questions to the extent possible and state your reasoning about what happens to the wave physically. A, what happens to the speed of the wave? We know that's going to decrease because it's going to colder air. B, what happens to the frequency? That's going to stay the same. And C, what happens to the wavelength? Well, as it gets colder, because the velocity's decreased, the waves are going to bunch up, and so the wavelength will decrease too. Okay, but it's asked us to give numerical answers where possible, so let's do that now. Okay, so the initial temperature was 27 degrees C, and then the final temperature is equal to 0 degrees C, and we have the frequency is equal to 4.00 kilohertz. And part A asked us for the velocity. Well, the velocity at 27 degrees is equal to 331 times the square root of 1 plus 27 over 273. Solving that on the calculator, you end up with 347 meters per second. The velocity at 0 degrees C is just going to be 1, so it's just going to be 331 meters per second. B, the frequency doesn't change, so we move from one medium to another, so 4.00 kilohertz at 27 degrees C and 0 degrees C. And C, we were asked to calculate the wavelength. But the wavelength at 27 degrees C is equal to the velocity at 27 degrees C over the frequency, which is the 347 over 4,000. That gives us 0.087 meters, or at 0 degrees, it's equal to 331 over 4,000, which gives us 0.083 meters. Next, the faintest sound the human ear can detect is a frequency of 1000 Hz, corresponds to an intensity of about 1 times 10 to the minus 12 watts per meter squared, which is called the threshold of hearing. The loudest sound that the ear can tolerate at this frequency corresponds to an intensity of 1 watt per meter squared, the threshold of pain. Determine the pressure amplitude and the displacement amplitude associated with these two limits. Okay, so initially our intensity is equal to 1.00 times 10 to the minus 12 watts per meter squared, which is I naught, and the frequency is equal to 1000 Hertz. And we're asked to find what's the pressure differential and the displacement. Okay, so we can use the equation I is equal to delta P max squared over 2 rho V. We just need to substitute into this equation. So we've got delta P max squared is equal to 2 rho Vi, which is equal to 2. Now this is air, so the density is 1.2. You'd be given this on the formula sheet. The velocity of sound in air, we usually take the standard value as 343, and then the intensity 1.00 times 10 to the minus 12. That should be a 12. Solving that on the calculator, we end up with 2.87 times 10 to the minus 5 pascals. And S max, to relate the pressure and the displacement, we can use P max is equal to rho V omega S max. So S max is equal to 2.87 times 10 to the minus 5 with the density 1.2 times the speed 343 times the angular frequency 2 pi times 1000. And solving that on the calculator, we end up with 1.11 times 10 to the minus 11 meters. A very small displacement, so it's not surprising that we can only just detect that. Okay, now in the second case, we had that the intensity was equal to 1.0 watt per meter squared, so a much larger number. All we need to do is substitute into these equations in exactly the same way. When we do that, we end up with the maximum pressure is equal to 28.7 pascals, and that S is equal to 1.11 times 10 to the minus 5 meters. Okay, and finally, a point source emits sound waves with an average power output of 80 watts. Find the intensity 3 meters from the source, and B, find the distance at which the intensity of the sound is 1 times 10 to the minus 8 watts per meter squared. Okay, so we've got some 80 watt source in here. It's transmitting sound in all directions, so they're traveling out as spherical wave fronts like this. And we're asked, we're now at a distance of 3 meters, what is the intensity? Well, intensity is just equal to power over area. So this is equal to the 80 over the 4 pi r squared, and r is 3 meters. So solving that on the calculator, we end up with 0.707 watts per meter squared as our answer to A. Now for part B, it says at what distance will the intensity be 1.00 times 10 to the minus 8 watts per meter squared. Okay, so we've got that 4 pi d squared is equal to, just rearranging this, the power over the intensity. Okay, so d squared is equal to power, which is 80 over 1.00 times 10 to the minus 8 times 1 over 4 pi squared. So d squared is equal to 636,619,772. Taking the square root, we end up with a distance of 2.52 times 10 to the 4 meters, which is 25.2 kilometers. So quite a long distance away. And that's the end of this lecture.